Hello everyone, hope you are all safe and sound. My name is Lina Yijiemao from Imperial College London. The title of the paper that I'm going to present today is Dirty Paper Coded Ray Splitting for Non-Orthogonal Unicast and Multicast Transmission with Partial CSIT. This is a joint work with my supervisor, Professor Bruno Clerckx from Imperial College London. My presentation today includes 5 parts, so let's directly go to the first part, introduction. In non-orthogonal unicast and multicast transmission, there are 2 different services, namely unicast and multicast services. Unicast refers to the transmission of a message that is only intended to a single user, so it's a one-to-one transmission. Multicast refers to the transmission of a message that is intended to multiple users, so it's a one-to-many transmission. In 4G and 5G, there is an increasing demand for a mixture of services. Conventional approach is to separate unicast and multicast on 2 orthogonal resources. Due to the scarcity of resources, a more recent approach is to superpose unicast and multicast messages in the power domain. The benefits of such non-orthogonal transmission is that the bandwidth and transmit power can be utilized more efficiently. However, it introduces additional interference between unicast and multicast messages. There are 2 conventional architectures in non-orthogonal unicast and multicast transmission. The first one is the conventional multi-user linear precoding. In MULP, the multicast message W0 and the K unicast messages W1 till WK are independently encoded into K+1 streams. The streams are linearly precoded and superposed at the transmitter. So here is the transmit signal. P0 and the PK are the precoders for the corresponding streams. At the receiver side, each user first decodes the multicast stream by treating interference from all unicast streams as noise. Each user then uses one layer of SIC to remove the multicast stream. After that, each user decodes its intended unicast stream by treating interference from other unicast streams as noise. So we know that in this conventional architecture MULP, one layer of SIC has to be used so as to separate the unicast and multicast streams. There is another architecture studied in the literature of information theory. It's known as data paper coding with superposition coding. In this architecture, the multicast message is directly encoded into the multicast stream as 0. But different from the previous MULP, where the unicast messages are no longer independently encoded. So in DPCRS, in DPC assisted scheme, the unicast messages are encoded by dirty paper coding. At receiver side, each user still decodes the multicast message as 0 and the intended unicast message SK sequentially with the assistance of one layer SIC. Such DPC-assisted strategy has been proved to achieve the capacity region of non-orthogonal unicast and multicast transmission where there are 2 users in the system and the transmitter knows perfect channel state information of the users. Both conventional strategies that I mentioned previously require the transmitter to know perfect channel state information of the users. Their performance drops quickly as CSIT decreases. However, as we know that such strict CSIT accuracy requirement is actually very difficult to be achieved in current and future wireless communication networks due to the increasing number of antennas and access points. Therefore, such dilemma motivates us to come up with a novel transmission strategy that is robust to the CSIT inaccuracy. In our previous work, we proposed a linearly precoded strategy based on ray splitting. Here we illustrate the K-user one-layer RS-assisted architecture. The private messages of each user is first split into a common part, WCK, and a private part, WPK. The common parts of all the users are combined with this multicast message into a super common message, WC, and encoded into a super common string, SC. The unicast private messages WP1 till WPK are then independently encoded into K private streams. There are in total K+1 streams linearly precoded at the transmitter. At the receiver side, each user first decodes the supercommon string, extracts the intended multicast message and the common part of the unicast message here. Then one layer of SIC is employed to remove the supercommon string from the received signal. Each user then decodes the intended private string. As the supercommon string has to be decoded first, contains both multicast message and a part of the unicast messages. The function of SIC is further exploited in rate splitting compared with conventional multi-user linear precoding assisted architecture. SIC in this linearly precoded rate splitting scheme is not only used to separate unicast and multicast strings, but also to manage interference among unicast streams, since we achieve to partially decode the unicast streams and partially treat unicast streams as noise. We have shown in our previous work that such linearly precoded rate splitting scheme outperforms conventional multi-user linear precoding, and most importantly, such scheme does not require any extra SIC at the receiver side. Only a single layer of SIC is needed. Another motivation to the work that I'm going to present today is from our previous work for unicast-only transmission. So in the unicast-only transmission, where each message is only intended for a single user, we propose this dirty paper-coded rate splitting scheme, where the message of each user is split into two parts, and we use dirty paper coding to encode the private parts and the superposition coding for both the common and the private strings. And we have shown through the numerical results that dirty paper coded rate splitting, which is the purple curve here, is able to outperform the two conventional architecture MULP and the DPC, as I mentioned previously. It also outperforms linearly precoded rate splitting, which is this orange curve, and the power domain normal, which is this yellow curve. Therefore, the performance benefits of dirty paper coded rate splitting in unicast-only transmission motivates us to apply dirty paper coding in non-orthogonal unicast and multicast transmission. So next, I will introduce you the system model that we propose. In this work, we consider a base station equipped with NT transmit antennas serving K-single antenna users. And we assume that each user knows perfect channel state information of which is perfect CSIR. But due to the imperfect CSIT CSF feedback or delay, transmitter only knows partial CSI. Here is our partial CSIT model. H hat is the channel estimate known at the base station. H tilde is the channel estimation error. HK here is the real channel of each user K. In this work, we assume that the noise power is increasing with SNR or transmit power. Alpha can be interpreted as the feedback bits. When alpha is equal to 0, the error power is equal to 1. So it's known as the constant feedback bits. And when alpha goes to infinite, the error power becomes 0. So the channel estimate is equal to the real channel, which is perfect CSIT. Actually, alpha equal to 1 already is already perfect CSIT in the DOF sense. Here is the first architecture that we proposed, which is called one-layer dirty paper coded rate splitting. The transmitter transmits one multicast message, W0, and a K unicast messages. Each unicast message is first split into a common part and a private part. The common parts of the unicast messages are combined with this multicast message into a super common message W0C, which is encoded into S0 and precoded by P0. The splitted private parts of the unicast messages are linearly precoded, but they are precoded, encoded, and precoded by dirty paper coding. So here is the resulting transmit signal. At the receiver side, each user decodes the supercommon string and the private string sequentially with the assistance of one layer SIC. So each user first decodes the supercommon string by treating the interference from the private strings as noise. Here is the instantaneous rate to decode the supercommon string. When SIC is used to remove the supercommon string from the received signal. The received signal becomes like this. As DPC is employed at the transmitter based on channel estimation, H hat, there is residual interference from users encoded before user pi k due to the channel estimation error. So due to CSIT inaccuracy, the instantaneous rate at user pi k to decode the private string is illustrated here. The architecture can be further extended to the multiple layer of rate splitting. So different from one layer DPCRS that we just introduced, we further split the message of each user into more different parts in order to form multiple layers of common strings. In this example, we illustrate the 3-user case. The message of each user is split into 4 parts, and 1 part of each user is combined with the multicast message into a super common string. Other parts are combined among different combination of users and form different layers of common strings to be decoded by different group of users. And the private strings are still encoded based on DPC. And receiver side, multiple layers of SIC is employed to sequentially decode the common strings. Compared with 1-layer DPCRS, the complexity at the transmitter and the receiver of MDPCRS here is much larger, but we will show in the results that MDPCRS achieves better performance. Next, we show the problem that we are going to solve for 1-layer DPCRS and the algorithm that we propose to solve it. Our target is to maximize the weighted ergodic sum rate of the unicast string subject to the QoS rate constraint of both unicast and multicast messages. It has been shown in our previous work that such weighted ergodic sum rate maximization can be then equivalently converted into a weighted average sum rate maximization problem, and for each channel estimate h hat. So here is the definition of the average rate at user k to decode the super common string and the private string. For a given channel estimate h hat, we take the expectation of the instantaneous rate over the distribution of h. In another word, over the distribution of error. So in this problem, we aim at designing precoders and the rate allocated to the common strings in order to maximize the weighted average sum rate. For each user, the average rate contains 2 parts. One part is the average rate of the private string. The other part is the contributed part in the transmission of the super common string. C hat here is the vector containing the portion of the common strings allocated to each message. To maximize the weighted average sum rate, the C hat has to be jointly optimized with a precoder. The first constraint is to make sure that the super common string is decodable at each user. The second constraint is the QoS rate constraint of the unicast strings. And the third constraint is the QoS rate constraint for the multicast message. This problem is non-convex, then the expectation here leads to a stochastic optimization problem. To solve the problem, we first transform the stochastic optimization problem into its deterministic form by using sample average approximation method. And then the problem is equivalently transformed into a WMMSE problem, which can then be solved by using alternating optimization. Due to time limitation, the algorithm is not further explained here. Next, let's look into the numerical results that we obtained by solving the problem I just explained. Here, we illustrate the ergodic rate region of the 2 unicast strings subject to QoS rate constraint to the multicast message. SNR is 20 dB, and there is 2 transmit antennas at the base station and serving 2 single antenna users. The QoS rate constraint is 0.5 bits per second per hertz. Sigma 1 square and sigma 2 square here are the variance of the circularly symmetric complex Gaussian channel for user 1 and user 2 respectively. When sigma 2 square is equal to 1, the 2 users have equal channel strength in average. When sigma 2 square is equal to 0.09, there is an average of 10 dB channel strength disparities between the users. In both figures, we can see that linearly precoded rate splitting, which is this orange curve, outperforms dirty paper coding, which is the blue curve here. The rate region of DPCRS, which is the purple curve here, it outperforms all other strategies. By using DPCRS that we propose in this work, the rate region of unicast streams in multi-antenna non-orthogonal unicast and multicast transmission is further enlarged. We further illustrate here the influence of CSIT in accuracy. As we mentioned previously, CSIT in accuracy is controlled by the power of CSIT error, and the power of the CSIT error is controlled by alpha. CSIT becomes worse as alpha becomes smaller. And we can see that as alpha becomes larger, CSIT becomes better, and the dirty paper coding, which is the blue curve, becomes better. It's closer to our proposed DPCRS scheme. However, as CSIT becomes worse, especially when CSIT becomes much worse in this region, the performance of DPC drops quickly. It's even much worse than the DP linearly precoded ray splitting schemes that we proposed in our previous work. So in comparison, our proposed MDPCRS, which is the red curve, it outperforms all other strategies. Therefore, we can draw the conclusion of this work. We first show that all linearly precoded ray splitting is able to outperform conventional dirty paper coding assisted strategy if CSIT is sufficiently inaccurate. And at the same time, linearly precoded ray splitting has a much lower hardware and computational complexity compared with DPC. Secondly, we show that the proposed DPCRS works well in multi-antenna non-orthogonal unicast and multicast transmission. It outperforms all the conventional strategies and is more robust to CSIT inaccuracy, network loads, and user deployments. Therefore, based on this study, we can obtain a bigger picture for NOUM. The problem we studied considers imperfect CSIT, which embraces perfect CSIT as an extreme case that when alpha goes to infinite. Secondly, the transmission framework based on ray splitting outperforms the corresponding no ray splitting counterpart. By turning off the common string in ray splitting, we reduce it to the two conventional architecture that I mentioned at the beginning. Therefore, RS is actually a more generalized, powerful, and promising strategy for non-orthogonal unicast and multicast transmission. This is the end of my presentation. Thank you for your listening.